Thank you very much, Pat. Thank you. Yes, so for those of you who've invaded from damped, I should say that this talk is primarily aimed at people who don't understand statistical mechanics as well as some of you do. Directed percolation. It's al. So almost everything I'm saying is in these two papers, which are review articles. Physics 2002 and Lubeck. J mod is 2003. So nothing I'm saying is much is much less than 20 years old. A little bit if we get onto it in the second lecture. I'm going to start with something called the contact process. And we'll turn to dp itself in a minute on a cubic lattice. So let's say one dimension initially. What do I have here? So at some time, I have a lattice, which I'm going to draw like this, and some of the sides are empty, and some of them are full. And in an infinitesimal time interval, things can happen. And the first is, if I've got a site which is empty next to a site which is full, it can become full. So if you think of these sites as people and the full sites as people with a cold, that's an infection. And it's going to happen at the rate lambda over 2. So lambda over 2 dt is the probability of that event for any two sites which are in that configuration. Likewise, of course, that one. I can also have recovery, which I shall draw this way. So I have, say, two initials. Well, the next four drawings are all recovery, actually. So let me just put them all here together. So one of those two can recover, or the other one, or the only one that I've got who's infected can recover. So these are recovery, and they all have rates a half. Obviously, I can rescale these rates in various ways. The important thing is that there's a ratio of an infection to a recovery rate, which will determine whether this epidemic survives or not. So I'm going to put this down and then I'll bring it back up. Actually, no, I can do it. I can reach. Just. So in d dimensions, I'm not going to reach like that for very long. I can think of a probability, so I can also think of these as zeros and ones, say, that depends on the number of infected neighbors, which is going to be called n. And this is lambda n over 2d in d dimensions. So n is the number of, shall we say, live neighbors. And W1 goes to 0 for any n is 1. So, please. Yes. Sorry? You could, it wouldn't make any difference, but you don't have to here. If dt is, the idea is if dt is small enough, only one thing happens in an infinitesimal increment. So it's yeah. Because I didn't draw them right. That's simple. At least I can answer that question. Yeah. So if I think of this in 1D, there's some critical lambda. This I'm just telling you, and it's 3.29 something. And for lambda less than lambda critical, so if I'm not, infections are, not happening quickly or easily, the infection dies out. With probability 1. And if lambda is bigger than lambda c, it has a non-zero, or a positive probability of surviving indefinitely. Caveat in an infinite system. I will come back to this point. If I have a finite system, there's always a chance that in a relatively short run against probability, everybody recovers, and then the game is over. Okay. So that's the contact process. Yes, absolutely. I'm saying P as a function of lambda well, this is a different P. See, this is the dying out P. Yeah, bottom one is positive. It vanishes at lambda c and stays at 0 for lambda less than lambda c. Okay. So so one of the mysteries about directed percolation is why on earth is it called that? It's the name of a whole class of in the same way as this one, but it happens to be BP that gave the class its name. But let me at least say what the relation is. It also leads to a very confusing notation in which time is treated as though it was a space direction, which is not helpful. So here I have a set of, so I've got to say a d-dimensional lattice again, which I shall now draw. And it has some infected or occupied sites. So it's something like that. Then in this direction, which if you want to think of this as, a rock, and it's got fluid on the top, and the question is, does the fluid make it to the bottom? So this is called x parallel. The lattice has this annoying thing of being rotated by 90 degrees. So the next layer of sites is here. And suppose I have this next. So the way this can be thought of is as bonds between lattice sites. And let me just carry on for one more layer. I'm just drawing an example. That one's going to split. This one's going to die. This one will go on like that. So at any place I could put a bond, I'm only allowed to put a bond if one of its upstairs neighbors is occupied. And I do so with probability P. So bond probability P. If side above is full, and the bond has to connect from a site that is full, then in this case it's extremely similar to the contact process. There's now a PC, not a lambda c, for which what I've said is the same. So as for lambda c. So I can think of this direction as time, and in most of the cases that I'm going to talk about, that's what it will be. But the reason it's called directed percolation is you can also think of this as a purely geometrical construct of a set of connections like the pore space in a rock. And if you take that mentality, then this is a special direction. That's why it's directed, because actually it has the logic of this layer determining what might happen in the layer below, which is not a natural perspective on percolation for people who are used to ordinary percolation. Still, that is what's called. So x parallel is time-like in that sense. Another way of saying the same thing, I mean, this is Markovian. in that direction. As I said, what happens in one layer. If I know what's in layer A, then I know the probability of anything that I could write for A plus 1 or X parallel plus 1. Yeah, so that's where directly comes from. Okay. So say a bit more about what happens. In this picture here, what you see is this kind of thing. And I shall now zoom out and just draw it with some lines. So I have essentially birth and death, or splitting and death, I should say. And this is the kind of process that it looks like. And I can define the correlation length in this direction, which is really time, as I've said. So that's better to think of as correlation time, but anyway. And in this direction, this is perpendicular. So remember, there are d dimensions here potentially, although one is interesting already, and only one in the parallel direction. So if I think about this one, so I can think of that as the correlation time, or length, but if I think of it as time, it's the mean time to die, if lambda is less than lambda c. So if lambda is less than lambda c, everything's going to die eventually. I can just start somewhere and say, well, how long is it before my descendants are dead? So that's that. And for this, it's the correlation length for the density. So I'm defining a density rho of x perp, which is, well, of occupied sites. Occupied / infected sites. And I can average this over the randomness of the actual choices of whether a bond is open or closed with probability p. It's traditional to think in Fourier space for this, rho q, rho star q, and this is going to be some function of q times that length, that correlation length, or in real space, rho r, I shall now use r for my x perp coordinate, r prime, minus mean value of rho squared, is another function now of r over c parallel. So what happens is, close to the critical point, these lengths become big, both of them. So things nearly die out. They last a long time before you can't even tell whether they're going to die out. If this becomes sufficiently big, they become correlated space-wise as well. The system develops a very interesting and highly clustered structure where you have clusters of infected people, if you like, and then a big gap to the next one. It's actually a fractal in that direction at the critical point. So it's the spatial structure of this that is interesting. And as I say, for today's talk, and I think for all of you, the interesting structure I'm talking about is mainly a slice at fixed time. Well, the time dependence is also interesting. Okay, any questions on what's so far said? So, critical behavior. So StatPhys people are very used to thinking about critical phenomena, and this is such a thing. And they get rather obsessed by things called critical exponents. And the reason they're obsessed with them is because these are interesting numbers in the sense they're not usually nice numbers. They're often, things that you can not easily calculate, but end up being highly reproducible in the sense that many systems that have a similar type of dynamics will have exactly the same critical behavior. So, critical. So, and I'm going to write these with lambda So I'm thinking of the contact process, but I could do it entirely in terms of P for directed percolation if I wanted to. So near lambda C, so near the critical point, or rho C, etc. If I look at the average density, so the fraction of average of occupied sites in some very large system, so this is the same as that, and this behaves like lambda minus lambda C to the power beta, so it vanishes that way. I'm interested in coming in from a positive value of this quantity here, but the modulus signs are kind of traditional in this field. So that's the density. I can also define something I'm going to call P, which goes like lambda minus lambda C to the beta prime. And this is the probability that some site is in what's called the infinite cluster. Infinite only in the sense that it's infinitely persistent in the time direction. So again, that's an unfortunate bit of language from percolation. This correlation length, namely the time correlation, has another exponent, lambda minus lambda C minus nu parallel, and this is blowing up as I approach the critical point. The perpendicular one, a further exponent, again, blowing up. I can also look at correlation functions. So this thing here, I'm going to call C rho of R. It's a function only of the modulus. Well, this R is R minus R prime, so I should have been more specific here. So I'm now going to use the notation R for that separation. This decays in distance like R to the minus D plus 2 minus eta. And there's a function of, I'm going to call F rho of R over C perp here. And the same, if I take the Fourier transform and I get this object, which is nearly always called S of Q in this field, this goes like Q to the minus 2 plus eta. Again, some other function, Fs, say, of Q C perp. So these are the kind of things which stat mech people are very much used to thinking about, close to the critical point, for instance, of a ferromagnet, a system which becomes magnetic at some critical point, is not magnetic beyond it, and has similar kinds of behavior of, in that case, I mean magnetization, but here it's at the density that is behaving with a non-trivial power law, etc., for the correlation functions and the correlation lengths. Something I can also do, though, in this context of the contact process or directed percolation, is think of a slightly different thing, which is to start with a single seed. So if I start with an empty space, these are all steady state properties. I should have written that up there. Excuse me, I'm not going to reach up to do it. Let me just put this now. In steady state. Right. So I can also think about explicitly time-dependent quantities. Now, there's various ways to do that, but one of them is to imagine that I have just one infected individual, if you like, and I ask, what are the statistics of the resulting epidemic? So from a single infected site, and I'm now going to use T, where directed percolation insists on using X parallel. So more exponents, I'm afraid. P tilde of T, T to the minus delta, again, some function which I'm going to call G P of T upon this quantity. So this is the survival probability. So I'm going to give that equation a name. So this is a late time. If you start with 1, you're very close to the transition. You may decay immediately, but you may make a decent sized cluster. Eventually, it will, if you're close enough to the critical point, it will decay like this with a power law. And I can also define the density as a function of time that in the system that results from this starting condition, that's got another power alpha. So you'll get bored with these powers if you're not already. Luckily, they're mostly not independent of each other, but I'm just establishing what they are. So I already defined that. The number of particles in the cluster goes like t to the theta. Again, a function of t over that correlation time, and its size, t to the 1 over z, g r t over c. So when the correlation time is infinite, in other words, at the critical point, you get pure power laws here. If you're a little bit away from the critical point, it looks like a power law, and then it will settle into something which is, say, a constant. So this is the number of infected sites. And this is the cluster radius. Please. Infinite. Yeah, so this is a single site in yes. And that's indeed. And basically when it depends on whether this, well, it's the other length. C parallel is bigger or less than the system size. So in an infinite system, it can in principle carry on being a power law forever, but not a power law. Okay. So there are other exponents available, but you've had enough of those. At least I have. So generally 3 or 4 are independent. And we're going to choose those as beta, beta prime, new parallel, new perp. So an example of why they're not all independent. Let's write this here. If I match this one, and also I'm going to give a name to that one, onto the steady state. So the idea is if I'm very close to the critical point, this time is very long, it will do this power law thing, but eventually, at this time scale, it will reach a steady state, and the steady state is described by those laws up there. So that says that if I know what is what the density is doing in steady state, it's doing a beta, then at large enough t, this has to cancel, the t has to cancel, which means that this power is the one that cancels the t's, and that tells you that alpha is directly given by beta modulo a factor of nu. So that matching there says delta equals beta prime over nu parallel, or alpha equals beta over nu parallel. I can also get z equals nu perp over nu parallel, etc. So you can define lots more exponents than you need, but it's important to realize that there are all these connections, this web of connections linking them together in the neighborhood of the critical scaling. Okay. Any questions on that?
Yeah.
Please.
Everything you say in D dimensions,
yes.
D can be a fractal domain?
No.
Got to be.
D is a proper piece of Cartesian space. Yeah. You can, of course, pose the problem in a fractal domain, but you then have to say exactly what it is. It's no good just saying what its dimension is. Well, it needs to know, you need to know the, if you could do it for a Sierpinski gasket, which is, you know, then you can ask these questions, and that has been looked at actually, but it depends on a lot of the exponents of the Sierpinski gasket, not just its fractal dimension. Yeah. There is, however, one more exponent, which is the fractal dimension of the cluster. So in one dimension, say, that's a set of points, but it's like a Cantor set. It's a set of points with very large gaps and very dense clusters. So that's itself a fractal. So let's squeeze that in here. So again, I'm talking about this as of the cluster. It's not really a cluster, it's a set of occupied points at time t, and this is df equals z theta plus delta. I'm definitely not going to derive that, but just to say it's one of the many things that you can talk about when you know the exponent. Okay. So one final thing about a dp and its exponents, which is a peculiarity, really. So note, for dp, or the contact process, beta equals beta prime. So only 3 independents of all the ones that I've mentioned so far. There's a reason for that, which I don't want to dwell on at all. And that is with the directed percolation process, with that kind of funny lattice which is on its side, I can reverse the arrows and turn it upside down. And if it's a realization of the dp process in the forward direction, reversing the arrows and rotating it 390 degrees is also a realization. So there's this kind of strange duality, which means that there's a link between the density and the survival probability. So if you start at the top, you can ask what's your probability of surviving to the bottom, and then you turn it around and that's the density of surviving of initial sites that propagate. So I don't want to try to explain that, partly because I don't fully understand it myself. So turns out that there's a transformation basically which maps whatever I call P tilde onto rho on doing this. So that's a detail, but it just means that there's only really 3 exponents here for these particular problems and ones like them. Okay. So that's what I want to say about these dimensions and the fact they're all linked up by scaling. I want to now talk about absorbing states. So if there's any questions about this, please ask.
Yeah, can this be formulated in continuous time and continuous space?
Coming up. You have to coarse-grain it. So you end up with a stochastic PDE, which if there are any pure mathematicians present, will say that doesn't mean anything, but I'll talk about that. Yeah. Okay, so I can hide that because it's a detail. Absorbing states. So the point about this is that if I have an empty lattice, it stays empty. And that's because in the models, both the models I've described, there's no spontaneous creation of particles. Or creation of infected individuals. This is crucial. If that was not true, there would be nothing. This would be just, all of these exponents would be totally different from the whole business would be completely changed. This is a crucial factor. So the idea then is that all of this criticality stuff, so spatiotemporal criticality, emerges in close proximity to this state, which is called an absorbing state for obvious reasons. You can get into it, but you can't get out of it once you're there. So close proximity here will mean very low densities. So the critical behavior of this type of model is what's happening when I have a very low density of particles, because they're only just enough of them to propagate the infection to the next generation, as it were. Okay, so let's put that up here. So you're always going to be close to this absorbing state. And in fact, that means that in a finite system, you'll always fall into it eventually. So let me try to explain that point. So the rate for this process of recovery or full becoming empty is always finite. That's why I was able to set it to 1 or half or whatever I did set it to before. So in a finite system, and I'm thinking in space and time here, so I can talk about a system size, L, and I start with some initial density, which is not even, it needn't even be close to 0 in principle. So there's a survival time before I reach this absorbing state, and I call that tau, but it's basically the same as C perp, which is independent of the system size if lambda is less than lambda c. In other words, if I'm below the threshold, everybody is slowly dying out, or even quickly dying out if I'm way below the threshold. So the survival time for the entire epidemic, if you want to call it that, is finite and doesn't actually depend on how big the system is, because there's a kind of systematic drift towards 0. If, on the other hand, I'm on the other side, what happens is this becomes a function of L over C. And what it means is that if my R number is bigger than 1, so if everything is basically tending to expand, then I have to have a very rare sequence of events to kill everybody off. But with a finite number of individuals, that event, that kind of composite event in which everybody recovers, still has a finite probability. It's exponentially small, but it's finite. So, but it does depend on the system size. So this requires a rho of n. So against the run of probability, and typically you expect this function to be something like exponential of the total number of sites. So that would be L to the, well, U to the D, where this variable is U. So that basically says that you have an extremely long time to wait for this. And if the system is infinite only, this time is strictly infinite for lambda greater than lambda c. If I start from a single infected site, let's put this here. Or in fact, any finite number. Hello? Yes? Yeah. And you can put bounds on them. The point is that if you think of that sequential updating thing, you could either do parallel updates or you could do a random update, but there's a finite probability if you've got n sites that you go kill, 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 kill. And that's an exponentially unlikely but non-zero probability. Yes. It's not self-averaging in that sense. Yeah. Which I think is probably different from undirected percolation, actually. because in high, well, at least maybe that depends on dimensionality, but that is the case here, at least as far as I understand it. Okay, but closely related to that is single seed again. So probability of this is now everybody dying out is always positive. Very similar statement. And this is what I was saying earlier, probability of survival as t goes to infinity is positive if lambda greater than lambda c and the system is infinite. So typically, if you start with lambda greater than lambda c and a single seed, there's about a 10% chance that you'll just die off immediately, and then an exponentially decreasing chance that you'll grow a bit and then die off. Much more likely you'll just grow. But as long as you stay finite, there's still some finite probability that you will die again. So the typical behavior in these rare events have to be distinguished. What you'll generally see here is just this ever expanding cascade of infections. Okay, any more questions on that angle? That's the way I would prefer to define it. It is defined for the infinite problem. You could, for the finite one, if you want to define, I think with directed percolation, I'm not even sure you can define it properly for a finite system. So the thermodynamic limit, the limit of an infinite system, is quite heavily built in to all of this analysis in terms of the scaling and so on. So I prefer to think of that critical parameter as whatever it is in the infinite system limit. Right. 4. Universality. So this is why any of this matters to a fluid dynamics person. Many microscopic models become the same, in quotes, on coarse graining. So in the language of the normalization group, which I will not use too much, they differ by irrelevant terms. And one of the wonders of the normalization group is that this word has a proper technical meaning within it. So models that differ by irrelevant terms form what is called a universality class. And the whole of the class shares the set of exponents. Also, incidentally, these scaling functions that I'm calling G's and F's. So this is a pretty important concept. And I will hopefully have time to make that more, flesh that out next lecture probably. But meanwhile, there's an even stronger statement in the context of the universality class defined by the contact model or directed percolation, which are basically the same, and certainly they're in the same universality class, and I will say more about why later. But there's a stronger statement than ordinary universality, which was made by Grasberger many years ago, which is this infamous DP conjecture. Grasberger, or maybe Grasberger and Janssen. DP conjecture. So, a single universality class, which is named after DP, describes all models with, and then there are a set of criteria. So I say this is a strong statement even for people who are used to the idea of universality classes. First criterion, there has to be a continuous transition. From a fluctuating active phase to a unique absorbing state. And there are plenty of cases that you can construct where the absorbing state is not unique, and all the ones we know about are not in this universality class. No, that's wrong. Many of them are, but there are exceptions based on that criterion. Second, you have to be able to think about, so continuous, by the way, all of this stuff, all bets are off, all of these scaling laws, everything. If you have a transition which is, you'd call supercritical, I suppose, if you're a dynamical systems person, but where instead of having the diverging correlation length and the system smoothly transitioning from one phase to the other, if you just jump, then all of this, there's no exponents, there's no universality to talk about, at least at the level I'm describing today. So continuous really matters, and uniqueness of the absorbing state also matters. Described by a positive one component order parameter, e.g. a density. So a density of particles is fine. There might be transitions where you had intrinsically needed two densities. I'll come back to one of those maybe next time. And there might be ones where the order parameter has some kind of vectorial property. And if that's true, again, that is an exception. I mean, that does not satisfy this criterion. And the third one, which I think is pretty important from the point of view of the fluid mechanics setting, is that all interactions, well, let's say all rules. So all the dynamical rules governing this density have to be short range. That doesn't mean you couldn't be in the class if they're long range, but it means that if you have long range interactions, you don't have any particular expectation to be in the VP universality class. Yes. I think, well, short range in this kind of setting usually means some kind of power law. So really infinite range in a sense. The point is that if the correlation length is diverging, so anything which is still there in the infinite correlation length limit may matter, and that could include like a Coulomb interaction. And it might include compressibility, or incompressibility rather. But if you have anything which has an exponential decay on a finite length scale, as long as the correlation length gets bigger than that, you should be back in. Yeah. So, and the fourth one is a little bit of a catch-all. No additional symmetries. Or conservation laws. French disorder. So you could be suspicious of this because it looks like a random list of things that people have discovered mean that it doesn't work. But that list has not actually grown for a couple of decades, so it seems to be stable. Yeah, so if you put in a random field, something which says you're more likely to get infected if you're here, again, that breaks this. So let's put that. I don't want to lie on the ground any longer. Quench disorder is a term which usually comes from magnetism. And it basically means you've got a random magnetic field that is permanent at each point in space. So if you had the rates k or lambda were themselves functions of position and not time, that would be quench disorder. So in a epidemic context, that makes perfect sense, right? If you live in a supermarket, you're more likely to be infected or something like that. Rather ridiculous example, sorry. The quench order, though, again, is something that you could imagine being realized. If you had, say you had turbulence in a one-dimensional pipe flow and the pipe is not of uniform width, that's quench disorder. You better worry about that. So I'll just give you a quick list of in and out, and then I'll start talking about the continuum picture, which will take us through to next time as well. In. DP as I've defined it, contact process, which is the very first model I talked about. Lots of other reaction-diffusion models. But without spontaneous creation, for the reason I've said. Otherwise, you don't have an absorbing state. So, for instance, NA goes to N plus MA, where A is a type of particle, and N and M are both positive, and A goes to 0. So this is just some generalization of this process whereby if you've got a particle, you can make more. If you have one particle, it can die, but you can't make a particle out of nothing. Rather few experiments, at least for a decade or more, people were wondering why actually there was not much evidence of DP exponents showing up in the lab, but that did change, so say until 2007, which was Takeuchi. So that was on liquid crystals. And I think is a chaotic flow in liquid crystals. I think it is connected with turbulence of those, famously pipe turbulence. So that's Lemieux, Nature Physics, 2017. And I think it's fair to say this was predicted by Sipos and Goldenfeld. Certainly Nigel was involved at some stage. And there's a paper from them on, that may not be quite the right reference, but anyway, it was, yeah, so then obviously there's this question about locality here. That's the question mark as to why these might not be in, but experimentally they appear to be in. Let's have a few outs. Again, more next time on these. So anything with creation ex nihilo. Ex vacuo, because that's not got an absorbing state. There are variants of DP or contact-like processes where the particle number changes by an even amount. So A goes to 3A, 2A goes to 0, A does not go to 0. And these are out because there are two absorbing states. And it looks a bit weird, actually, because if the particle number can only change by +2 or -2, then I begin with an even number or an odd number of particles, and this stays the same forever. So each of those only has one absorbing state. But there are two different absorbing states that the system can see if I look at a patch of it, where then the number of particles in that patch could be odd or even. And I'll say more about that later. So this is, and so the fact that there are two absorbing states here, one is basically empty, and the other is a single A. changes everything completely in a way that is quite unintuitive. So I will try and say more about that next time. Yeah. There's also something called conserved DP. So here I have what we're now going to call active and passive particles. And an active particle can turn a passive particle active, and an active particle can turn passive, and diffusion for A, not P. So what happens here is you have these two species of particles. The absorbing state is reached as the active particles die out. But as they do so, they leave behind a load of passive particles, which used to be active. And depending on where those end up, because they are now passive and not moving, each of those possible arrangements of passive particles is a different absorbing state. So that again is definitely out, and this definitely has different exponents and totally different behavior. Interestingly, there is a set of experiments for this, which basically is called random organization. So that's Corte. What is... so what you have there is you have a set of suspended particles, it's like the kind of classical G.I. Taylor experiment. Suspended particles, they're not Brownian, so they're big enough that they can't diffuse, and you shear them oscillatory like this. And depending on the amplitude of the shear, they either bash into each other each cycle, or they don't. And then you kind of strobe it. And as they pass through the origin, some of them come back to exactly the same spot because they've not had the collision. Others do not. And if you keep doing this on what is initially random initial conditions, and depending on the magnitude of this oscillation, there's a critical amplitude of that, which leads to this transition. So as a function of that amplitude, you either stuff keeps moving forever, or you end up in the absorbing state where every particle does not collide with another during the cycle. That absorbing state is one of an infinite number of where the particles could be, and that has exquisite correlations in it. So this is actually the DP-like system that I personally have been more interested in recent years. Okay, it's 5 to 5. What would you like me to do? I could just spend a few minutes, maybe as a kind of taster, saying what the continuum theory looks like, and then we'll talk more about it next time. Okay, let's do that. Sorry? These are the tests. These tests are clearly much more easily applied to a theoretically defined model than to any kind of lab experiment. Yeah. Well, for me, the question mark is it short range? Is the interaction between puffs short enough range? I think in 1D, that feels in pretty good shape because the pipe has a kind of way of limiting the interaction. I think it makes the one-dimensional character of the pipe would make puffs more independent. In other words, the question is whether, say, a splitting of this patch into two turbulent patches cares about the distance to the next one. And for me, that's more credible in 1D than in 2, but nonetheless, the experimental picture is it seems to be fine, right? Yeah. Yes, but that's then you're making the mistake of thinking the order parameter is the fluid velocity, which is not. The order parameter is the density of some object that characterizes the turbulence. So what you need to think of is you need to imagine that there's a coarse-grained description of, if you like, the turbulent density or the number of turbulent patches. And the question is whether the interaction between those things can be viewed as short range. So it is quite a subtle question. That's one way to say it. Yeah. Well, wave propagation can come from local interactions, of course. I mean, it does in a crystal. So I'm not sure I'm totally ruling that out. Yeah. I think you have to distinguish between short-range interactions and short-range effects of interactions. So I wouldn't say wave propagation was a sign of long-range interaction. Yeah. No, that's one of the most difficult things. Basically, because the continuous transition is about the neighborhood in some parameter space, you've got some kind of bifurcation. And you could always have a reason why that is just totally undercut by something that's happening between a state over here and a state over there, so that you never see this. So that's a limitation of the whole of this branch of statistical mechanics, which deals with critical points on the assumption that they exist. Yeah. Okay, let me just give you a taster then of the continuum description. So this is statistical field theory. It's a bit of statistical field theory. So the stuff of statistical mechanics courses, but it also is basically SPDE, stochastic partial differential equations. So if I coarse-grain, say, the contact process, and you can go through a laborious procedure to actually do this, but hopefully the result will be intuitive. Rho is the density of my things, minus k rho, that's decay. So that process is there. Lambda rho, 1 minus rho. So this says I can create a particle, but if you think of the process I defined at the beginning, I need to have an empty site beside me. So there's a nonlinearity here, which doesn't look like it's going to matter much at low densities, but maybe, well, we'll see what happens to that next time. So that's contact. Process, if you like, is the probability of that. Then you need this, d del squared rho. And it's interesting because I've not mentioned diffusion, but there is diffusion always in these models. And an easy way to say that is if I start here and I infect my neighbor and then I recover, I have moved. So that pair of processes means that there is a diffusion going on as well. These terms on their own, nothing would move. There would be no sense of propagation in that sense. And a noise. So I'm going to give this a star because I'm going to come back to it. So this is noise. So I need to say a little bit about the noise. It will be multiplicative. You're one step ahead. So yes, the noise can't be independent of density. And the reason is, or a reason is, that the density has to stay positive. So as you approach very small density, the noise has to get very small. Otherwise, it would just take you across to negative densities, and that's definitely the wrong physics. But actually, one can be more precise than that. It's called demographic noise. So underneath this is this discrete process on the lattice, say, which is a Poisson process. So I'm microscopically Poisson, but that's not going to survive into this coarse graining, and it doesn't need to, for reasons connected with universality, which I'll talk about next time. So I have discrete events. So this coarse grains into local Gaussian white noise. So the idea is that the coarse grain scale, there's lots of these little events locally. I've zoomed right out. There's lots of stuff going on. And the sum of all these Poisson events can be viewed as a Gaussian process. So the question then, what is the correlator of that process? And it's going to be local. So CRT, this is zeta, isn't it? R prime T prime equals, I'm going to write it this way. There's a gamma, And there is a row, so this is indeed multiplicative. And then delta function r minus r prime, delta t minus t prime. So those of you who are used to white noise are used to this. And the other thing is that gamma is directly proportional to kappa plus lambda. And the reason for that is the noise is dominated by if I take the low density limit there, I can forget about the nonlinearity here. I've got a decay, a death rate, kappa, a birth rate, lambda. The average rate is the difference, but the variances are additive. So the noise here comes from the randomness in that process. So those two bits of randomness add. So the variance is the sum of the variances of these two Poisson processes, which are both equal to the mean rate. That's basically why this comes out. Well, that means that this quantity here doesn't have any interesting behavior close to the transition, but that factor does, because the density is getting very, very small. Okay. And it's important that this is linear. But linear noise doesn't mean it's linear in the equation. It's a horribly nonlinear term. But it's important that that is a row to the one. Let's just emphasize that. And indeed, some of the out models that I described, in particular the one where the particles only go up and down in two at a time, this ends up being squared. So it's a completely different model for that reason. Okay. So also present, but ignorable and indeed irrelevant in this specific sense that I will elaborate a bit next time, is diffusive noise. So this is demographic noise, but as long as I have diffusion, that d del squared rho term is the mean of a stochastic process. That's the mean effect of diffusion, but that also means there's noise connected with that. So diffusive noise, and that is basically, I'm going to constantly drop the arguments here. I have a d, because unsurprisingly it's proportional to the diffusion constant, and it's actually got a Laplacian here, which is pretty horrible. But in Fourier space, it's fine. ZQ, ZQ prime, T prime equal to dq squared, delta Kronecker Q prime, delta T minus T prime. So it's actually fine. Right, but of course something isn't fine. And I'll just finish with this. Where shall I put it? Get the equation back down here. Now let's just place it here. Big caveat. So stochastic PDEs like that one make no mathematical sense. A prime. The problem here is not the multiplicative noise, it's the fact that because the system is noisy, rho becomes rough, and this Laplacian doesn't necessarily have a meaning. So what you need, which I'm definitely not going to talk about any beyond this sentence, is regularity structures if you're a pure mathematician. For which Martin Heyer got his field medal in 2014, which certainly for me is the most interesting field medal from a physics point of view since Witten. This is hard. It's basically an exact way of doing the renormalization group, which I'll say a tiny bit about next time. It's hard, and the reason you're hard is that you need to know the exponents beforehand. So there are very few models, not including DP or the contact process, for which actually say in one dimension, you know that beta is 2/3 and the nu is a quarter and whatever. If you know those exponents, actually what Heyer is saying, and what he does his field medal for, is saying that you have to take the continuum limit in this strangely singular way that reflects all that power law stuff that I told you about at the beginning. But anyway, I'm not going to talk about that because the way physicists have dealt with this for years is you have a cutoff. So there's some minimum spatial length scale, a lattice parameter, say. And this gives me some Q max. So what that means, once I put a cutoff, is that that equation is basically just shorthand for a finite, but large, stochastic differential equation system. So that's how one bypasses this otherwise huge en passe. And Hira couldn't have got past this en passe without knowing how the renormalization would work over here. But then, and importantly, you seek properties that are independent of the cutoff. And that includes, and specifically focuses on, the exponents that I described before. Okay, so plan for next time. I want to talk about the mean field theory. So there's an approach to this equation which treats the noise as somehow small, and turns out that that is actually adequate in dimensions bigger than 4. When dimension is less than 4, you have to do something much more messy and physicsy with the renormalization group, which I won't do in any detail, but I'll at least indicate. And in particular, the renormalization really, for me, and I think many physicists, is actually the explanation of why universality exists, why there are big classes of different model which all have the same critical behavior, at least in the sense of the exponents. And this, again, is connected with this idea of terms being relevant or irrelevant in a way that the renormalization group tells us how to define. So that's the plan for next time. Okay. Happy to take more questions, of course. Sorry to overrun. Yeah. Yes.
So there's two things. One is the global nature of the equation. The other is that there's a determinant.
Yes.
Everything you talk about, the
Yes. Well, so there's two views of that. One say, okay, well, statistical physics is stochastic. The other view, though, which is a bit more fundamental, is that to even get close to this kind of equation, you have to do some coarse graining. And it's very important to realize that if you coarse grain a deterministic equation, you get a stochastic equation, always. You may approximate it with a deterministic equation, because you must have terms that you've neglected and you don't know what they are, and they must be able to vary. And so those terms, if you're honest, will always appear as some kind of random term in your coarse grained equation. So for me, coarse graining itself implies stochasticity in the coarse grained description. But not everybody would agree with that, but that's the way I view it. So one of the ways, I don't know whether you know much about liquid state theory, a way of coarse graining, which goes back to Zwanzig and Mori and people in the 50s and 60s, is called projection operators. And you say, I'm going to have some slow degrees of freedom, which I'm going to follow. And I'm going to have these fast degrees of freedom, which I'm going to eliminate. And explicitly, the fast degrees of freedom appear as a noise kernel in the coarse grained equations. So that's an explicit construction which leads to that effect. But what I'm saying is that if you've coarse grained, there are terms which are not zero that you don't know and are not watching. So there'd better be some kind of stochastic term in your equation if you want to keep all the physics you might have. Of course, in any particular situation, the noise might not matter.
Okay, I don't know, maybe.
Mm-hmm.
But DNS. One of the questions can do. And so you could justify that even if you could imagine that's true for the reason I gave in my talk about chaotic failure.
Yeah.
But some of my colleagues think that we're doing finite precision arithmetic, and what we're seeing is, in fact, coming up, with excavating digits from noise.
Yeah.
And that's what we're seeing, and that's part of it.
I think I'm on your side in that debate. I mean, once you've got a nonlinear equation and you don't keep complete resolution, I mean, Greg Heineck was here a year or so ago, and obviously has his different views about this, but you can't follow the Navier-Stokes equation with complete resolution. So you have to admit that you've either accidentally or consciously discarded some very fine scale information. And I'm much preferred to think of doing that consciously, rather than just say, well, I'm doing my very best with these numerics. And one of the reasons to do it consciously is then you have a chance of, actually saying how it might behave and what it might do. Yeah. But I mean, obviously, if the system is sufficiently chaotic, it doesn't matter what you do at the short scale. And that becomes a question about the nonlinearity. And once you get to a script like this, you can ask, is the noise relevant? In this setting, it is. Otherwise, you couldn't have a Poisson processor, you see.
Classified as a damped, noisy Fisher equation.
Yes.
Right. So it begs the question, could it have additional pieces in the form of a divergence of a flux of some form? Because the Fisher equation comes in families of that structure. In some sense, where have they gone? You mentioned Maurice-Wanzig, but that, of course, dovetails to Fokker-Planck in certain limits, which includes a divergence of a flux, usually.
Well, I mean, okay, so I think it's very important to separate anything which looks like Fokker-Planck from anything like this. This is a Langevin equation. If you want me to write down a Fokker-Planck equation for that equation, I can write it down. It's not very helpful. But in the deterministic part, those are the terms which come from the contact process or direct percolation. Yes, but then as I will claim next time, there could be, say there was a term which creates particles out of the vacuum, that changes everything. But there's also lots of terms I could add which make no difference. And that's back to this idea of universality. Yeah. Yes. No. Conceptually, there's a very clear definition of what a critical exponent is, how it emerges, and this is what one of the things the renormalization group does without necessarily being able to calculate them accurately. And it also creates this idea of, so basically in the renormalization group, as I'll try and say a bit next time, you have a way of viewing the system which allows you to access the critical point in such a way that you can talk about the flow towards the critical point from wherever you start in the space of models. And so this defines a map, and the map has a fixed point at the critical point, and the eigenvalues of the map, when you linearize it about the fixed point, are the critical exponents. So there is it's certainly measuring them as a pain, but there is a precise sense in which it does mean something to say they are the same for these two models, because basically when I do this procedure on those models, they flow to the same fixed point in the renormalization group. And I will say a bit about that next time. Yes, you look at the space of models, and you basically, that space of models under this renormalization group transformation has a basin of attraction in which all these models, when you zoom out close to the critical point, converge on a single set of behaviors, which are the critical exponents. So you can't think about it without thinking about the connection between different models. In other words, embedding the models in a space where you can move between models. The universality doesn't make sense if you can only think about one model. You have to think about the set of all possible models. Yeah. Yeah. Yes. Multiple absorbing states and a conservation law, and actually two order parameters. Anything else that, Jim? I think there may be models which you can formulate as the dynamics of a single scalar, but they still have a multitude of absorbing states. But the version of CDP, which I like to think about, where you have active and passive, obviously has two species. Yeah. Okay. Thank you.